Right. So for today, we will first try to introduce alternative interpretation of the binary regression. We introduced the logistic regression, but logistic regression is just one form of binary regression. So just as a recap, for the binary regression, we will have the response variable not as a real value random variable, but yi as binary. That's the setting. And we have some data like that. And using the random versus systematic structure we introduced throughout this lecture, we assume that yi are independently following its own Bernoulli distribution with its own probability parameter pi I. So as you know, pi I just indicates the chance of getting one, and it's between 0 and 1. And for the systematic structure, just as the generalized linear model, we want to assume the mean of yi, which you know is generally denoted as mu I, which is defined as expectation of yi. In this special case, it's actually pi I. For the systematic structure, we just assume that some transformation monotone function g applied to the mu I, here we just write pi I, is a linear function of our predictors, xi transpose beta. So this is the linear part. And the distribution goes from Gaussian to Bernoulli. It's called generalized. So that's why it's generalized linear model. And also the generalization of the distribution would also let us generalize this G function. For linear model, the G function is just the identity function, no transformation. But now we use the monotone transformation. So here we want to discuss some other types of binary regression besides logistic regression by focusing on other forms of G. Recall that for logistic regression, we have a specific form of G. Maybe we can pull this forward a little bit. Yes. You remember where this was attached to? No, the part is so short. Maybe let's this one. Use that after. I think that's this. You can see the screen better. Let's just wait for it to respond. It should be on. Okay. Mentions. Okay, so let's continue. For logistic regression, we have the specific form of G. G of pi I is actually log of pi I over 1 minus pi. And we have written this for many times, and we call this function a logic function. The key is that we want to map, we need a G to map from this interval 0 to 1 to the real values. That's what we need. Okay, but to help us understand other types of binary regression, if you recall, I mentioned the probit regression, which is defined as by defining a G as G of pi I as the inverse of the CDF function of standard normal. So this is the ECDF of the standard normal distribution. Okay, so we also map this interval 0 to 1 back to R, because any CDF function will map whatever domain the distribution is. And here for standard normal, domain is R, real line, to the 0 to 1 interval. That's in general. So probit regression uses the inverse of the CDF to achieve that. But to generalize, to consider other possibilities, we will provide this interesting, I would say, formulation of binary regression. So we consider this to be a latent variable formulation. I want to say that this kind of thinking, let me hide this panel because it's not really right loading. Okay, so for latent variable formulation, I want to say that this is something very general in statistical modeling. Sometimes we will introduce the latent variable to help us understand the structure of our data. So here the formulation is that we consider yi to be observable binary response. But we believe that underlying the data, there should be some yi star, which is the latent continuous response. So we want to assume that this yi star is just taking a real value. And why is this a reasonable formulation? If you think about those voting data, if we have one person I, who vote yes or no to a question, maybe underlying this person I's mind, there is some continuous decision. It's just depending on where the threshold is, then the decision may become yes or no. Just like if we choose a candidate, when we vote for an election candidate, you may have some preference for either candidate, but the preference might be 51% for candidate A, 49% for candidate B. Well, for another person, it might be 90% for candidate A, 10% for candidate B. But your decision might both be voting for candidate A. So that's just a thresholding effect. In this formulation, then we assume that yi is just the dichotomized version of yi star. So it's like some indicator function that yi star, if it's greater than theta, some threshold theta, it becomes 1. Otherwise, it becomes 0. And in this formulation, theta becomes an additional threshold parameter. But how do we ensure that this parameter is uniquely identifiable? So there's one issue we must consider. Because yi star is a latent variable we assume, And theta is also something we don't know. So both can change. And you can see that if you apply the same scaling and shifting to both sides, yi star and theta, we have the same indicator function. That means I can multiply yi star by some positive a and shift it by some b. If I do the same thing on theta, it's the same indicator function. Nothing changed, which means that if yi star and theta can vary freely, there's no unique way to link yi star to yi. So therefore, for simplicity or for identifiability, because it doesn't matter what A is, what B is, so therefore, we set for this identifiability, which is something we also consider a lot in our modeling. We set theta to 0. We can just set it to 0. And also, we can set this continuous latent response yi star to have variance equal to 1. We can set this. So then there's no ambiguity in terms of the scaling and shift. So therefore, you see, we would have yi just as the indicator function of yi star being positive. Okay, and then we can borrow our linear model for the latent continuous random variable. So if we assume that yi is xi transpose beta plus epsilon I. This is a linear model. Then we can assume that the binary response actually comes from the linear yi star, comes from the linear model, then truncation. Because we can do shifting. It's just for identifiability. Like I said, we assume yi star to be anything. You can assume it to be y star. You can assume it to be a times y star plus b. So the shifting and the scale can be anything, right? So then we can just set the threshold to 0. It doesn't matter. Yeah. I think this kind of mindset is also very important when you do modeling. You need to know what parameters are necessary, what can actually be removed. Sure.
I mean, we think of like latent response to be like with respect to each response, like with response under like the 0 response versus like the response is 1.
What do you mean? So you're talking about the observable response, that is binary.
Yeah.
But the continuous response is what's latent, what's underlying, what we don't observe.
Yeah, I'm trying to say that there's like a latent response for the observed being 0, and then an additional latent response variable for the observed being 1. And after that, the comparison with the doing like a yi star 0 or a pi star 1.
What's the benefit of doing that? Because the latent variable is what you assume, right? You want it to be easy to work with. So basically, this formulation is trying to go from linear model to binary response model. What you think is that, okay, maybe in the data generating process, there is some underlying linear model with a continuous response, but we don't get to observe that continuous response. We only observe the binary appearance, which is a truncated version. Yeah, which actually happens a lot, like I said, in the social science problems, like the voting. People have to force themselves to do a binary voting, even though what they really have as the response is continuous. Yeah. Okay. All right. So then using the linear model as y star, then what is our pi I? So let's see this. So for linear model, one thing we know we want to assume is that this is the random part, just as a quick recap. This is fixed, no randomness, and yi star is random. So knowing what is fixed, what is random is very important, especially in the last part of this class when we talk about linear mixed effect model, that becomes crucial. Okay, so normally as random variables for the error term, we want to assume that epsilon i's are IID following some distribution. And remember, for linear model, that distribution is assumed to be normal with a constant variance. But here we want to be more general. So we set it to be some distribution F. But in most cases, we often, or in most cases, we assume the mean of epsilon I to be 0. So that we believe the error term's expectation is 0. It fluctuates. So with these, then as yi is the indicator, if we are interested in the pi I, in the binary response formulation, which is the probability that yi is 1. That's the Bernoulli parameter. Then it translates to the probability that yi star is positive. Then we put in the linear model for yi star. It translates to epsilon I is bigger than negative xi transpose beta. It becomes this. And if we use the formulation, the notation we have for generalized linear model, remember, if I scroll back here, we give this a name. We call the linear predictor. We call this eta I. So we use the eta I just for simplicity. Xi transpose beta is eta I. Then coming back here is the probability that epsilon I is bigger than negative eta I. Okay, here, when I write this distribution F, let's put it as the CDF function for some distribution for our simplicity as the CDF. Then this is essentially what? This is essentially 1 minus the probability epsilon is less or equal than negative eta I. And this is the definition of the CDF. So it's 1 minus CDFF at negative eta I. That's my part. And if I have this additional assumption, if the distribution F is symmetric about 0. So here I'm not talking about the CDF being symmetric. I'm talking about the corresponding density function being symmetric. When that happens, for example, Gaussian distribution, right? Normal Gaussian distribution satisfies this about 0. So in this case, we actually know that probability epsilon I bigger than negative eta I is equal to the probability of epsilon I less than eta I. So you have the two tails being equal to each other. So in this case, then pi I can be just written as probability epsilon I less than eta I. And that's the CDF function F applied to eta I. So of course, this is under the assumption that F is continuous. Okay, symmetric about 0 and continuous. It's a continuous distribution, but it's reasonable to assume the error terms to be continuous random variables. So it should be obvious. Oh, sorry. So then what do we need? You see, don't forget that what we need is to discuss the length function, right? We need this G of pi I being eta I. Linear predictor, G of pi I. So then this formulation, I would say this one, if I label it 1 or 2, they could give me a way to find G. Okay, so from 1, I can see that the G, I just solve for 1, right? So for 1, I use it to solve for what is the pi I that will give me what is the g of pi I? That will give me eta I. So basically, I'm solving this pi I equals 1 minus f negative eta I. So solving for eta I, it will give me g of pi I as negative f inverse 1 minus pi I. That is eta I. Okay, so I have 1 g pi I in this way. That gave me a general form of the link function. And from 2, if I use the simplified form, I have pi I as f eta I. Then this will directly give me g of pi I, which is just f inverse pi I, will be eta I. So I get the link functions. So therefore, no wonder probability regression is one special case. So let's look at the 3 examples. So depending on how we specify the f, the distribution for the error term, we can get the corresponding link function. So that's why this latent variable formulation generalizes our discussion for the link function for binary response regression. So example 1, f is this thing. What this means is that we have epsilon i's IID standard normal. Okay, when we have that, and also normal distribution naturally satisfies 2. So 2 poles, right? Because it's symmetric about 0. So then we have G is F is the phi inverse because F is phi. And this is probit regression. Okay, that's the first example. That's why in the old days, I would say probit regression has become very popular because of this natural connection to linear model. We just assume that error terms follow linear model. We use the latent truncation thresholding formulation for binary regression. We get a probit regression. But as you can see that in our earlier introduction, we talk about canonical link functions using the exponential family theory. And logistic regression, logic function satisfies the canonical link function, but not the product. I think that's the one reason why later people just use logistic regression. And also because for exponential family GLM, we have this iteratively reweighted least square for solving the problem. That's what we covered a few lectures back. That also gives this logistic regression an advantage for using the canonical link function. Okay. Because you see for this one, remember for the optimization, we have G prime. We need this. And in this case, the G prime will be inverse CDF prime. And this is difficult to compute. Okay. That's the example 1. Example 2, let's see what is the distribution. What is the distribution that logistic regression corresponds to? So for logistic regression, you see that we have eta I as log pi I 1 minus pi I. Then we write the equation as a pi I equals something. And we show that we can easily see exponential eta I 1 plus exponential eta I. That's it. Then we want to link this pi I to eta I function, this function of eta I, to some distribution CDF function. And this is something actually we want to introduce. So if we define the CDF function fx just as exponential x to 1 plus exponential x, and x can take real values. This CDF function is defined to be the CDF of a distribution called logistic distribution. CDF of logistic distribution. This is something we define. And if this logistic distribution is something you haven't heard of, it's good to do some Google to see what it looks like. In short, it is a bell-shaped distribution, just like the normal distribution, but it has heavier tails than the standard normal distribution. So this one has heavier tails than the standard normal one. So it's a more heavy tail distribution. And if we know that, okay, so if we have this, so if we write epsilon i's are IID logistic distribution. And of course, it can have its own parameter for tuning, but here we're just using the most standard one, so there's no other parameters. If it follows this logistic distribution, then we can have some natural property. The variance of eta I, the mean is just 0. This is same as normal distribution. Variance of eta I is pi squared over 3. Okay, and you can see that versus if you have epsilon I, IID, standard normal, as in our example 1, in the probit regression. In that case, we have variance of epsilon I just being 1. So like the two variances are not on the same scale. So therefore, to put it on the same scale in terms of the variance of the error term, we can write the logistic distribution as yi star divided by pi over root 3 plus equals to xi transpose beta vector divided by the scalar pi over root 3 plus epsilon I over pi over root 3. The reason we do this is just we want to make the error term to have variance equal to 1. That's the reason. So then we can compare this model to the other, the example 1's model, where the error terms have variance equal to 1 because they follow standard normal. So what I'm trying to say here is that if you want to compare the coefficients, beta coefficients you obtain from this second formulation, logistic distribution formulation, versus the normal distribution formulation in terms of the error term, we need to normalize the coefficient by dividing the factors so the error terms are on the same scale. That's very important. So what I'm saying here is that you need to compare beta, you need to compare beta hat if you get an estimate from the logistic regression. Logistic over pi over root 3. You need to compare this to the beta hat probit. That's important because they're not on the same scale. And that's something you will notice when you do this binary response regression in R. Because in R, later I'll say that there are multiple options. Default is logistic regression for the link function, but you can also specify probit. And there's a third one. The third one, which is also in the literature in the R function, specifies another distribution for epsilon I, F. So here, the epsilon i's are assumed to be IID Gumbel distribution, which is another distribution you might not have heard of. And the Gumbel distribution is also like a bell shape, but it's not symmetric about 0. Bell-shaped, but not symmetric about 0. That's the thing. So you can check it out. And regarding the Gumbel distribution, it's something we specify for mathematical convenience. And so a lot of the interesting distributions were invented for convenience and for easy derivations, for interpretations. So there are two ways to derive the Gumbel distribution, and they're both quite interesting. So two derivations of Gumbel. The first one is that if we have a random variable x that follows an exponential distribution with rate parameter 1. So this exponential distribution has domain just as the positive real values, including 1, but no negative values. So then we can have log x with the natural base follows Gumbel. So we can consider to be like a log version for the exponential distribution. I know you know the exponential distribution is not symmetric at all because it has this left bound at 0 and then the right can go to up to infinity, but it's not symmetric. But once you do the log, you're basically changing the domain from the positive real line to the whole real line. Okay, so you can have negative values in Gumbel. And it will make the shape more symmetrical than the exponential density curve. Second derivation is that if you have this, that's why Gumbel is sometimes called the extreme value distribution. If you have n random variables IID independently following exponential 1 distribution, and you define the maximum of them as x order statistics m. If you define this as the maximum, then the maximum minus log of m would follow, what we'll say, converging in distribution to Gumbel distribution. That is, the larger the n, the closer this term will be to a Gumbel distribution. So that's another way to derive the Gumbel distribution. But anyway, Gumbel is an interesting distribution. And if we want to assume that the error terms follow that, then we can have the CDF of Gumbel as fx being exponential to the negative or exponential to the negative x. So two exponential. So I can write as exponential negative x, like this. And here, x is still real values, real values. And what this means is that if you have a real value x, right, then you can easily show that, okay, exponential negative x is what? Think about the exponential function, and then you can see what's the range of this, because exponential is always positive, right? So it's like positive part, and negative or positive become negative. And for exponential negative, it becomes 0, 1. So that's how you change the thing to 0, 1 value. For this, because Gumbel doesn't have a symmetric PDF density function. So that's why when we want to go from this distribution to the link function, we have to use the first one. Pi I equals 1 minus f minus eta I. And this will give us this g of pi I is minus f inverse 1 minus pi I. We cannot use the second one because this requires symmetry. So using the first one to find a g function based on the inverse of the CDF, we end up getting then eta I is negative f inverse 1 minus pi I. So we find the inverse of this f function. It's actually, interestingly, log of minus log of 1 minus pi I. Okay, so let's see why this will be a reasonable link function. We know pi I is between 0 and 1. So 1 minus pi I is between 0 and 1. Log of value between 0 and 1 is negative. And then negative of this negative is positive. and log of positive value will give me the whole real line. So that's how we do the math. And this one has a very interesting name. It's called complementary log, short as C log. Link function, complementary log. And similar to our previous discussion about the variance of epsilon I given a distribution, right? We have the epsilon following logistic with the variance pi squared over 3. Epsilon I following standard normal with variance 1. How about here? When the epsilon I follows Gumbel distribution, what is the variance? Here, if we have epsilon ID Gumbel, we have the variance of epsilon I as pi squared over 6. So therefore, if you want to compare it to the probit regression, you standardize yi star by pi over root 6 equals xi transpose beta over pi over root 6 plus epsilon I over pi over root 6. That's it. Okay. And this model actually has a very interesting name in some literature called hazard model. So just to wrap up, if you want to compare the coefficients, it will be beta hat probit versus beta hat logistic over pi over root 3 over versus beta hat has C log, I should say. C log's the link function name over pi over root 6. So in R, in the GLN function, you have some arguments, but two things you need to specify. One is the family, which is about the random structure, what distribution. And here you want to say binomial. You know, binomial is the general form for Bernoulli, right? Bernoulli has n equals 1. Binomial can have n greater than 1. And once, if you remember, when we talk about the group data, grouped binary data, we use binomial. And also another argument you need to specify is the link. And here, some options, including logit, probit, and C log, which is what we covered over here. It's about the how to specify the link function. But nowadays, the default has become just to use the logit because of logistic regression being the canonical link function. Okay, so one more thing I want to say is the outlier detection. So this is just alternative formulation of binary response regression. But to wrap up our logistic regression discussion, going back to the model fitting diagnostics, remember in the previous lecture, we talked about two things. One is goodness of fit test, which we aim to study how well does the GLM fit to the data compared to the saturated model, which gives every yi its own mu I hat. Just yi is equal to mu I hat. We have the inference of data. Yeah. That's a very good question. I have to admit that I haven't seen any. Similar property. Yeah, but maybe it's not like you don't have this nice, how to say, so in terms of the link function, right? So you have to go through that CDF of the T distribution, and then you take you take the inverse of that, take the inverse of that. And then something worth considering, but it's very, very good question. And you should definitely do a check to see what you can find out of this. But I would say one thing interesting to know is that you need to also worry about this G prime in the optimization. What is something easy to work with? Yeah. Thank you. Yeah. I think one thing that makes the logic function attractive is that you can write as log minus log, right? It's a log ratio. And we know that log is something nice to work on for derivatives. Yeah. Thank you. Okay, so we talk about goodness of fit for the overall fitting of the model. We talk about inference when we want to say a particular beta hat J. What can it tell us about beta J? So something else we talk about for linear model is the diagnostics. So for diagnostics, which is something you did for your homework too, is basically outlier detection. You want to see whether some data points have large influences on your model, and whether you have good justification to not include those data points. That's what we mean by outlier detection. So for linear model, we work on residuals. Here, we also have residuals defined for generalized linear model. So we talked about two types of residuals. First one is called Poisson residuals. Unlike linear model, in linear model, we just have one type of residual. That's yi minus yi hat. But here, since the yi is not something that's linear or continuous, so here we need some other transformation to justify why it is a residual. The Poisson residual is basically defined as yi minus its predictive value, which is mu I hat for generalized linear model, because mu I is expectation of yi. Our estimate for mu I as mu I hat is what we predict for yi. But here to bear in mind that, let me just write it, yi minus mu I hat. To bear in mind that in the linear model, basically, you can roughly think all the yi's have the same variance sigma square, which is the variance of epsilon I, even though we know that y hat has that different variances. So that's why I put a residual. If you recall, the residuals don't have the same variance. You have to consider the hat matrix. It's actually 1 minus hii times sigma square. Hii is the ith diagonal entry of the hat matrix. That's what we have. But here, if you have, say, Bernoulli yi, or if you have binomial yi, so this difference will have very, very big difference in their variance. It's not just that hat matrix adjustment. So that's why for Poisson residual, we are dividing it by mu I hat ni minus mu I hat. So this is the group data, okay? Group data, if you recall, the ith group has ni observations divided by ni. Okay, what is that? What is this standard deviation? What does it mean? So just to give you some intuition behind it, recall that here for yi following each yi is independent binomial ni pi I. Okay, we had this. So therefore, if I call mu I as expectation of yi for such data, is actually ni times I. Okay, and for the variance of yi, what is that? It's actually ni times pi I times 1 minus pi. That's the variance formula for the yi. Okay, and you can see that this is essentially, if I write it as mu I, it's mu I times ni minus mu I divided by ni. That's why we have this. So that's how we do, we standardize the yi by its standard deviation. But we're doing plug-in because mu I is unknown, so we plug in mu I hat. Okay, so therefore, if we assume that the mu I is a good estimate, okay, assuming the plugin has good accuracy, and then asymptotically, we can have this thing as n goes to infinity, ni, so all the ni's will go to infinity. So the within group size will go to infinity. Let me just say here, ni goes to infinity. Then this will actually will go to standard normal distribution. Okay. So if you use the Pearson's residual, you would use the standard normal distribution to tell you roughly how big this is big. This is too big, right? Because standard normal distribution, we know that 95% of chance the values are between two, right? -2 to +2, or more exactly, negative 1.96 to 1.96. That's the 95% interval, covers the center for 95%. So chance. So therefore, the rule of thumb here, which is something we also use for linear regression diagnostics, is basically this thing has absolute value greater than 2. When that happens, we think the residual, Pearson residual, is probably too big, and this point is worth checking. Okay. Another thing is the deviance residual. The deviance residual will, by name, rely on the deviance. So what it actually means is that if you recall, the deviance is basically what? Do you remember? What's the deviance? It's likelihood ratio. Yeah, it's the -2 times the log likelihood ratio, right? So it really depends on the ratios for what and what. Which two models do you compare the likelihoods? For goodness of fit, we test is actually about the compared to the saturated model, right? So yes, so it's actually in the saturated model thing. So basically, I'm just saying deviance, as a recall, is the -2 times log of the likelihood of GLM and the likelihood of the saturated model. That's basically a deviance. It's about how well the model fits. And you know, like the mean squared error, the smaller the deviance, the better the model fitting. Okay, so here when we say deviance residual, we are defining it as, this is defined as the square root. I just skip the formula, just like say it's the square root of the ith term in the sum of D. So D can be written as a sum of I from 1 to n, sum over the observations. And I'm taking the ith term in the deviance sum and take the square root of that and call that the deviance residual. Okay. So roughly speaking, this is based on the fact that the deviance we know should roughly follow chi-square distribution with n minus p degrees of freedom. That degree of freedom is the difference in parameters, number of parameters between the two models. Okay, so we're basically trying to see how much of the deviance is attributed to the ith term by the ith observation, and then use that as a way to decide whether the ith observation is the culprit, is the one that makes the deviance big. So that's the intuition underlying the deviance residual. And there's a similar rule of thumb by checking whether this is bigger than 2. And of course, this is subject to some approximation to say, okay, this is approximately normal. So then that's the rule of thumb. But just bear in mind that when we say rule of thumb, it's never something accurate. It's more like just an empirical criterion with some sort of intuition or justification to justify what we consider as big. But ultimately, when you detect outliers and when you decide whether they should be removed or not, it's always subjective. Yeah, so that's why I feel like the domain expertise of your data kicks in here, because you need to decide what you want to reserve or you want to throw away. And so I think for now, transparent data analysis, the most important thing is to be transparent and accurate and record everything you have done. Because it's possible that your decision here might play a big role in your decision, in your storytelling. Okay, so that's what I want to say about logistic regression, GLM diagnostics. And furthermore, I think something I hope to add as an interesting note is this property. So there's a property, good to know, that also generalizes from the linear model. So this is a property of exponential family GLM with canonical link function. Okay. What is this property? It is actually X transpose Y equals X transpose mu hat. Just this very simple, it's sometimes called normal equation for a linear model. So this X transpose is P by N. The transpose of our design matrix, Y is N by 1. So same on the right-hand side, P by N, N by 1. So essentially, what it says is that for each predictor, if you take its N values and do the inner product with the response, it's the same as the inner product with the predicted response. So why is this something good to know? Because remember, the first predictor in the design matrix, the first column of X is all the ones, right, for the intercept. So the first row of X transpose is all the ones. So this implies that the average of Y's is always equal to the average of mu hats. So that's this. This is implied by the equation. This is. And for linear model, we know this already, but this also holds for generalized linear model. And why is that? The reason is because of optimization. It's because we use MLE to solve for beta hat, then we get this. So this reason is because we use MLE beta hat to give us mu hat. That's the underlying reason. And what does MLE imply? So this will trace back to the exponential family formulation. So look at the log likelihood again. We write this small l log likelihood at beta, which is a sum I from 1 to n, yi theta I minus b theta I. That's the exponential family density function we give you, ai phi plus c yi phi. Okay, and for the canonical link function, we satisfy that, if you still remember, theta I is eta I. We said this. That's how we derive that the link function G should be the inverse of the B prime. I remember it's the inverse of B prime. So because the expectation of yi is B prime theta I, right? So we go from there. That's how we derived it. Then with this canonical thing, this log likelihood becomes sum I from 1 to n, yi eta I minus b eta I ai phi plus cy phi. Okay. Okay, so now with this, we can further go from eta I being linear predictor xi transpose beta. We go here. So this is what we have seen before. I from 1 to m, yi times xi transpose beta minus b at xi transpose beta ai phi plus c yi phi. Okay, now it's time to take the derivative. Partial derivative against beta j. So I'm not doing the vector derivative, but just doing the partial derivative for one component of beta. Beta j, partial derivative of beta. Then you see inside the sum for the first term, because the inner product is like xi1 times beta 1 plus xi2 times beta 2 plus xij times beta j. So then only xij will stay because they are taking the partial derivative. So it's yi xij. Okay, same here. By the chain rule, I would have minus xij b prime, b derivative at xi beta, xi transpose beta, ai phi. This term is gone, and I will set this to 0. And this will be set to 0 for all the j from 1 to p. Then you see, by setting to 0, I have what? I have this interesting thing. So put the sum, because the denominator doesn't really matter because it doesn't involve, because we're just setting the numerator, to 0. So then what we can say here is that, let me see whether I can say that. Can I ignore the denominator? Okay, I think something I will just make a simple assumption here to keep it going because otherwise a little complicated. So let's just say that, let's just have this ai phi to a phi. Ignore the I here. Okay, that will make things easier for me. With this, then setting it to 0 would give me this summation I from 1 to m yi xij equals summation I from 1 to m xij b prime xi transpose beta. Okay? And as I know that xi transpose beta, or now I should put a hat here because I'm setting this to 0 to solve for my MLE. So because I know that xi transpose beta hat is by definition my eta I hat, linear predictor. By the canonical Pulling function is my theta I hat, the parameter, location parameter exponential family. So therefore, this is, I can say b prime theta I hat. And now I know because of the property of exponential family, this is actually the definition of expectation of yi. So this is actually my mu I hat. So things are linked in this way. So that's why for the right-hand side, it's I from 1 to n, xij, mu I hat. That's it. That's exactly what we are getting. So basically, the left-hand side is just the inner product between the jth column of the X design matrix transpose times the Y, inner product of those two. The right-hand side is basically the jth column transpose, so the jth predictors column transpose times mu hat, inner product. Oh, I'm sorry. Yeah, so that's what we have. And then we stack it row by row. That's how we get this normal equation. Okay, so how do we interpret this? So I'm just saying that X transpose, the design matrix transpose is basically one, maybe I just say X1 transpose to XP transpose. Yeah. But in particular, the first row is just once. So therefore, we have this X transpose Y being X transpose mu. That's what we have. So what I would say here is that besides the interpretation for the first X row, we have the Y sum equals mu hat sum. Besides this, we also have that if you have some categorical factors in your predictor, you know, when we talk about ANOVA, when we talk about the categorical predictor for linear model, something we said is that you will code a categorical variable predictor with say k levels by k-1 binary predictors, right? So with those binary predictors, if one of the rows indicate one level, then you will have some ones for the observations in that level and rest zeros. So that means that if you have categorical variables, then within the level, the sum of yi and the sum of mu I hat are also equal. So we have that matching. Okay, so I think this is a way to justify that using the GLM with canonical link function, you have this nice property that your predictors match your actual response, sorry, your predictor response match your actual response in this way. It matches overall as a sum, and it matches within each categorical predictor level, within that level by the sum. Okay, so I think that's just a nice property. Any questions before we move on for this? Hopefully, after so many iterations of those parameter transformations for GLM, now it doesn't seem that complex as before. Finally, we will introduce Poisson regression. Poisson regression is another type of GLM. So here, the yi's are counts. 0, 1, 2, up to infinity. Okay, so again, random structure. As the name stands, Poisson distribution. For such non-negative counts, the most simple or intuitive distribution to assume is the Poisson distribution. So if some of you haven't really thought about why is Poisson a natural distribution, it's worth checking. So there are some events happening in real life that just is Poisson, just like Gaussian, right? So I think these are the very natural justification of why they are reasonable distributions to assume about. Anyway, here, when we have the yi independently following Poisson distribution, there's a mean parameter mu I. Poisson has only one parameter. Very important property is that the mean and the variance are equal. And the mu I as a parameter is positive. So one thing I just want to say is that Poisson can be considered as an approximation of binomial. So this approximates binomial in I pi I. Okay, how does it do the approximation? So if we have ni goes to infinity, pi I goes down to 0, and ni pi I converges to mu I, the Poisson parameter. If we have this, then Poisson actually approximates the negative binomial, which means that there are many draws, and each draw has a diminishing probability of being 1. So the more draws you have, the probability of getting 1 is going down, but the overall number of ones is converging to this mu I. So in this is case where the Poisson approximates binomial. So you know, in the real life, a lot of events are like binomial, like coin tossing. But when they happen, frequently or not frequently, when the tosses happen frequently enough, then we can assume that we have infinite number of tosses, but actually the number of ones we get is actually stabilizing. It's not like we're getting infinite number of ones. This is the mu I, the kind of constant number for expecting the number of successes out of many infinite number of draws. So this is for events like this, for Poisson. So Poisson is one way to approximate negative binomial. That's one way to justify it. And coming back here, so even though I want to say that even though theoretically high I can take infinitely large counts, but it really depends on your mu I. If mu I is very small, and because you have expectation and variance both tied to mu I, then if mu I is small, very small, then there's almost no chance that you will get a very large count. Then your count will be concentrated on small ones to satisfy both. That's just it. Okay, that's the random structure. And as we have for logistic regression, the randomness in your response is only from the random structure. And the systematic structure will tell you, as long as two observations share the same covariance, exact covariance, then their mu I is exactly the same. So they're tied to be the same. But still, their yi could be different. And that's just due to the Poisson draw, randomness. So here the link function, which is the canonical link function. If you write out the Poisson as the exponential family form, then you can see that the link function as the inverse of the b prime function, it's actually the log function. This is xi transpose beta. And you can see that mu I being positive, but log mu I will be from negative infinity to positive infinity. So we satisfy that both sides are real values. Then we will just talk about the estimation, right? This is the Poisson model. And if we want to reiterate the IRLS for estimating beta MLE, what is the iteration? So this is another recap again. So let's say if we are in the kth iteration. So we have the parameter values for k iteration, the kth parameter values already. So first of all, we want to derive the working dependent variable, which is the z, to replace y. How do we do that? In each iteration, let's first get the working dependent variable. And we call that zik for the ith observation. So remember, that is the linear predictor given the current parameter values eta ik plus this additional adjustment term just from the Taylor expansion. So this is like a Taylor expansion center. This is the first order adjustment. Yi minus mu I k times g prime mu I k. That's the working dependent variable. Here we have g as log, right? So g mu I is log mu I. This is our link function. So therefore, g prime mu I is just 1 over mu I. And we'll use this g prime. So this is just eta ik plus yi minus mu ik times 1 over mu ik. Working dependent variable, that's it. Second, we need to derive the weights. Because without the weights, we cannot do the weighted least square. So we need a weight for the ith working dependent variable. We call that WIK, which is the ith diagonal entry in the weight matrix. by definition, is defined as 1 over the variance of zik. Okay? Variance comes from yi because eta I is supposed to be fixed. So it's just here. And we can actually see it's actually 1 over the variance of yi. Please note that the variance should carry k with it because we're using the parameter values in the kth iteration times the square of mu ik. Just the variance formula. And here, Poisson helps us. Y variance k of yi is just mu ik. That's the Poisson property from the Poisson. Poisson variance formula over 1 minus mu ik squared. Then it's just mu ik. That's the weight. Finally, we use the working dependent variable and the weight to update our parameters. So the first update we will do is the beta coefficient using the weighted least square. Beta k plus 1, the new value is just x transpose wk x inverse x transpose wk working dependent variable vector zk. So we stack z1k to znk as zk. That's the beta. And eta k plus 1. This is just linear predictor. Easy, right? X times beta k plus 1. We have eta. Finally, we need a mu. Mu I for observation I, k plus 1. It is by the inverse of the length function. It's just the g inverse eta I k plus 1. And here, as g is log, then g inverse eta I is exponential eta. We take the inverse of log, that's exponential function. Then here mu I k plus 1 is exponential eta I k plus 1. And here we have I go from 1 to n. That's it. So for Poisson, actually the IRLS, the whole procedure is actually a little bit simpler than for logistic regression. The reason is because the length function is just log. Okay, so that's how we basically review this IRLS again. So that's all for today. We'll stop here. And so next time we will just finish a bit of the remaining details of Poisson regression. Then we will talk about some generalization of Poisson regression to account for over-dispersion. That is, your count data may have, your data may show that the variance might be bigger than the mean, right? So this Poisson saying that mean and variance are equal may be not realistic. Then how do we account for over-dispersion? Okay, so for this Wednesday, we will have our special reader Guang Ao to go over the first two homework here. So if you have any questions about the two homework, please bring them here. And then if we have some time remaining, then we'll may play some the recording to continue discussion. But I will see you on next Monday. Okay, thank you. I'm still here. Yeah, we'll just meet here. I think it's just simple for everyone. Yeah. Thank you.